We have to start deriving the p-n junction current. To do this, we have to derive a fundamental equation called the current continuity equation. So in the previous video, we concluded that when we apply a forward bias equal to Vf, the minority carrier levels at the interface between the neutral zones and the depletion region increases exponentially. And so, whereas the equilibrium level of holes at the n side is ni squared over nd, this level rises to ni squared over nd times e to the power of qvf by kt. Similarly, on the p side, we see an exponential increase in the concentration of electrons just at the interface with the depletion region. However, as holes start to travel into the n zone and electrons that diffuse across the depletion region start to travel through the p zone, they start to see plenty of carriers of the opposite side. So the injected minority holes on the n side will see a lot of electrons. And so there's a huge chance that they will recombine with the plentiful electrons on the n side. Similarly, electrons that diffuse to the p side will quickly recombine with holes on the p side. This is why when we draw the profile of electron concentration on the p side, we see it dropping precipitously as we go deeper into the neutral zone and far away from the interface with the depletion region. We return back to our equilibrium level. And we also see something similar happening on the n side. This fast recombination is happening because of the plentiful concentration of the opposite type of the carrier. However, what happens here at the interface is still very important. The fact that we have a lot of minority carriers being injected is the main reason we see forward current in p-n junction. This is even though most of these carriers will quickly dissipate as we go deeper into the neutral zones. To be able to derive the current equation, the current in the forward bias p-n junction, we first have to derive something called the current continuity equation. This is an equation that deals with what happens to current if we pass through a region where there is excess recombination or excess generation. We're talking mainly about this area and this area where the excess carriers that have been injected are being absorbed in the neutral zones. So the let's talk about the n side, for example. So the concentration of holes at any point is equal to P naught, which is the equilibrium level of holes, plus delta P. And delta P is the excess concentration of holes which has been injected from the P side. So the excess concentration of holes is delta P. And if we take a small section, if we think about what the rate of recombination is in any material, the rate of recombination is going to be proportional to the excess concentration of holes. So the more holes we have, the faster the recombination. The less holes we have, the less the recombination. So if you push a lot more excess holes into the n side, you're definitely going to have a lot of recombination happening. So it's going to be proportional to delta P. But it's also going to be inversely proportional to something called the lifetime of holes in the n side. This is how long a hole can remain intact as an excess hole in the n-type silicon. And it's obviously dependent on the doping level in silicon in the n side, because if we are using heavy doping, the n side is rich in electrons, which can recombine with holes a lot faster. And so recombination rate is proportional to delta P by tau, where tau is a property of the n side, and it's a property basically of doping level on the n side. Now, let's look at a conductor. This conductor could be the n-side neutral zone or the p-side neutral zone, or it could even be the depletion region. This is just a general conductor. And we are going to try to derive something called the current continuity equation for this conductor. And it's basically talking about the continuity between j of x and j of x plus dx, which is the current exiting an infinitesimally short distance. So basically we are talking about what is the difference between j of x plus delta x and j of x. Are they going to be equal, or is there going to be a difference? And if there is a difference, where does that difference come from? So basically, when we talk about steady state current conduction in a piece of silicon, we were generally talking about j of x equaling j of x plus delta x. There is no difference between the current going into a cross section and the current exiting another cross section, because current in the steady state is equal through every cross section of the conductor. But in this case, we are talking about the fact that within this area, within this volume, within this small volume, there is something that happens to some of the carriers that enter the cross section. So the carriers that enter the cross section through j of x, not all of them manage to exit it as j of x plus dx. Some of them may die within, and these carriers die because they have recombined. And so we have to add another term here that accounts for recombination of carriers within this unit volume. So basically this is going to be delta p divided by tau times delta x. So we have found the amount of carriers that have recombined within this unit volume. So this unit volume is A times delta x, but we are calculating current density, so we don't multiply by A, and so it's just delta p divided by tau times dx. And what we are saying here is that the charges entering the cross section are going to be equal to the current or charges exiting the cross section, plus anything that gets lost in the middle because of recombination. So if we are talking about excess holes, in this case we are talking about the current that enters the n neutral zone through diffusing holes from the p side, and so we're talking about hole current. And what kind of current is this? This is obviously diffusion current, because we have excess holes diffusing from the p side to the n side. Now we have a missing q in this equation just to make the units work out. It has to be a charge, not a carrier concentration units. Now if we take the limit as dx tends to 0, we turn this difference equation into a differential equation, and so we end up with q delta p by tau is equal to minus jp of x plus dx minus jp of x divided by dx. Now taking the limit as dx tends to 0, we get q delta p by tau is equal to minus djp by dx. And this is the current continuity equation, which we will come to use quite often, so we have to keep track of it. Now the current we are talking about here is the whole current that manages to get into the n side. This is a diffusion current. If you recall, when we apply a forward potential, we lower the potential barriers for majority carriers on each side, allowing them to inject a lot of minority carriers onto the other side, which happens by diffusion. So this is a diffusion current. If we write the expression for whole diffusion current, it's minus q dp by dx. dp by dx is the gradient of the whole distribution profile, which if we look at the n side, is actually a curve and has a finite gradient for a long distance. So there is a diffusion current within the n side. Now if we take the expression of Jp and substitute in the current continuity equation, we obtain a second order differential equation, which is very useful and which is the equation we have to work with. So in fact, this equation will relate the hole profile to the excess hole concentration. And so this is the main equation we have to work with. Right, so this is the second order differential equation we have to work with, except that there's one problem with this, which is that it is relating delta p to p. So let's just think about what delta p is and what p is. So we are talking about holes on the n side that have managed to get into the n side. P is the hole concentration on the n side. which consists of Pn naught, which is the equilibrium level, plus delta P. And delta P is the excess holes that manage to get injected from the P side onto the N side because of the application of forward potential. And so we are relating two different things to each other. We want this second order differential equation to be an equation in just one unknown, either delta P or P. But let's just think about it for a second, because Pn naught is not a function of distance. It is constant with distance as long as doping is uniform, and its value is equal to Ni squared over Nd. And therefore, when we differentiate or take the second derivative or the third derivative or any derivative of P, this is equal to the derivative of delta P only, because Pn naught is a constant offset. And therefore, the true form of this second order differential equation we will be using is dp delta P by tau is equal to d2 delta P by dx2. And so this is the equation we will be solving, and this is the equation we will be putting most of our effort into. It is important to understand that there is also a similar equation for electrons on the p side. We will have dn times delta n over tau is equal to d squared delta n by dx2. Now, it's important to understand that the tau here is different from the tau here. We will call the tau in the top equation tau pn, and we will call tau in the lower equation tau np. What this means is it is the lifetime of holes on the n side. This is the lifetime of excess electrons on the p side. And so these two equations are the equations we will be working with to obtain the forward p-n junction current.